So today we are starting with biomolecules. In biomolecules, if I say, so biomolecules, we will have to do carbohydrate, then proteins, right, vitamins, and nucleic acid. Nucleic acid. These are the four subtopics in biomolecules for this week. So let's start with first carbohydrates. So carbohydrates, you can call it as if it is a hydrated carbon, H2OY, CxH2OY. So optically active polyhydroxyaldehydes and ketones or substances that hydrolyze to yield optically active polyhydroxyaldehyde or ketone are called carbohydrates. So either they should be initially as a polyhydroxyaldehyde or ketone, or they should hydrolyze to this ultimately polyhydroxyaldehyde and ketone, then they are called carbohydrates. So hydrated carbon, the word was derived from here, hydrated carbon. Carbohydrates are also called saccharides. Okay, they are also called saccharides. Now, in Greek, this word means sugar. In Greek, the word saccharide meant sugar. So that was what was used. Classification of carbohydrate based on taste. Like if it is sweet, then it is called sugar, table sugar, cane sugar. This type of name or this type of thing is for sweet carbohydrate. If it is tasteless, okay, no specific taste like wheat flour, rice flour, no specific taste in a dry flour, potato starch, then it is non-sugar. Sugars which are having a sweet taste and non-sugars which do not have any specific sweet taste. Second classification of carbohydrate is on the basis of hydrolysis product. Okay, like they can be monosaccharide, disaccharide, oligosaccharide, polysaccharide. So monosaccharide are the simplest carbohydrates which cannot be hydrolyzed any further. Then they are called monosaccharides. Disaccharides are those which on hydrolysis will generate two monosaccharides. Now these two monosaccharides could be identical or could be different. Okay, a particular sugar which on hydrolysis gives two monosaccharide, whether they are same or different, then it is called disaccharide. For example, maltose, lactose, this type. Trisaccharide, which on hydrolysis give three monosaccharide, same or of different type, then it is called trisaccharide. ठीक? Oligosaccharide, those carbohydrates which on hydrolysis will give 2 to 10 molecule of monosaccharide are called oligo. And polysaccharide is those which on hydrolysis will give more than 10, then they are called polysaccharides. So two methods of classification we have just done. Okay, one was based on number of monosaccharide that will be created or generated by hydrolysis of a particular sugar, and one was on based on their taste, whether it is a sweet taste or not sweet taste. Now classification number third, on the basis of their reaction with tolerance and Fehling. Okay, so as you have already read in aldehyde ketone chapter, that with tolerance and Fehling, it is the aldehyde part that will react. And what happens that the aldehyde part get oxidized and the tolerance reagent silver positive get reduced to Ag plus. That is the test. Now what happens in this process that the Ag plus of tolerance reagent is reduced to silver. When it is reduced to silver, Ag plus is reduced to silver. So it is reduced, so sugar is called reducing sugar, the one which can act as a reducing reagent. So it is called a reducing sugar. Okay. Similar in the Fehling, it is CuO which is present. So plus 2 copper is reduced to plus 1 copper. So it is reduced from plus 2 to plus 1. So here if any aldehyde can do this reduction, so So it is again called reducing compound. And in case of sugars, we'll call reducing sugars. Clear how to use that? So reducing sugars are those when carbohydrate can reduce Ag plus or Cu2 plus ions of tolerance or filling solution and itself gets oxidized, then it is called a reducing sugar. Non-reducing are those which cannot reduce tolerance or filling solution, then it is called non-reducing sugar. Okay, that is how the classification of carbohydrate on the basis of tolerance and filling is done. Monosaccharides. Now, till here we were classifying total carbohydrate. Okay, not the individual monosaccharide. Now, individual monosaccharide is further classified. How is it classified? It is classified first as aldose or ketose sugars. So, aldehyde group, aldose. If the carbonyl group in the molecule is aldehyde, then we call it aldose sugar. If the carbonyl group in that molecule is a ketone, then we call it ketose sugar. Okay. Oh, there is a spelling error. Aldehyde, single L should be there. Aldehyde. Okay. And ketose sugar. So if the carbonyl part of the molecule is aldehyde, aldose. It is a ketone, then ketose sugar. Now see D-glucose. Glucose is a aldose sugar and fructose is a ketose sugar. Okay. Classification 2 of monosaccharide is based on number of carbons present in that particular monosaccharide. If it has 3 carbon, triose, 4 carbon, tetrose. Let me write here example. For example, if I have say this, so total I have 3 carbon, so it is triose. Okay, and it is not that it has to be only aldose, it could be aldotriose, it could be ketotriose, like this, and so on, pentose and hexose. So number of carbons total present in a monosaccharide, based on that triose, tetrose, pentose, hexose sugars are used. Then comes the erythrose and threose sugar. Third classification of monosaccharide. Now, this erythrose threose is limited only to tetrose. Okay, this is a very limited application classification, limited to tetrose sugars. Okay, it is limited to tetrose sugars. Now, how it is to be used? See, we know that, and see, these are not identical. Here I am having W, here I am having M. So they are different groups, W and M, right? So for example, if I have aldose, let us consider if I have aldose sugar and tetrose, then I can have this type of geometry, right? Or I can have CHO, CH2OH, HOH, and OH. This type of geometry also possible, na? So what is happening? These are the different groups. Vertical line has different groups. Identical groups are placed on the horizontal line. Identical. This chiral carbon also has OH and H. This chiral carbon also has OH and H. So if out of those identical groups, I have OH and OH across the vertical line, then it is called trio pair. Why pair? Because there is no plane of symmetry. So definitely this is chiral. So its mirror image will also be there, na? Like this. So these are the enantiomeric pairs of each other and is then called trio pair. Now, if the identical groups are on the same side, see OH, OH, of vertical line, and then this and its mirror image, because again it is not meso, W and M are different, so it is not meso, then this is called the trio pair. So erythro pair and trio pair. Is that clear? Then comes the D sugars and L sugars. Reference is D-glyceraldehyde. Okay. D sugar and L sugar, this D and L is a terminology which is with respect to one particular chiral basic molecule taken, which is glyceraldehyde. Now, when we talk of this glyceraldehyde, what happens that in a correct fissure, okay, in a conventionally correct fissure from top to bottom, if OH is on the right hand side, then it is called D sugar, D glyceraldehyde. If this OH is on the left hand side, then it is called L glyceraldehyde. Okay, so whether it is a D or a L glyceraldehyde, this is how we decide. So D glyceraldehyde, L glyceraldehyde. Now, if I come here for glucose, what we do is we draw conventionally correct fissure. What is the conventionally correct fissure? The longest carbon-carbon chain should fall on a vertical line. The longest carbon-carbon chain should fall on a vertical line, and then the highest IUPAC numbered. See, 1, 2, 3, 4, 5, 6. So fifth we are talking. This chiral center we are referring to. The highest IUPAC numbered chiral center. If on that OH is on the right hand side, then it is a D sugar. If OH is on the left hand side, then it is called a L sugar. But remember, very, very important that D and L have to be compulsorily enantiomers of each other. Like, yes, glucose, this one is a D glucose, but I cannot call this as a D, say L glucose. No, just OH left mein rakhe, so it is not L glucose. For D glucose to L glucose, you have to have a mirror image relationship. See, D glucose, L glucose. Now, see, this is a complete mirror image. So this is called a DL pair. This is not called a DL pair. Okay. So they have to have enantiomer of each other. And here, when I talk of capital D, capital L, there is no meaning of small d, small l. Dextro और लीवो का कोई मीनिंग नहीं है. ओके, डी एल का कोई इसमें मीनिंग नहीं रहेगा. Structural representation of monosaccharide. So those were the classification of structural representation. As I said, fissure, conventionally correct fissure. So what is the way of drawing all these structures? So yes, when you draw a fissure, there is a fixed pattern or the method that you have to follow. What is that method? You have to compulsorily keep the longest carbon chain on the vertical line. That is point number 1. Okay, so you have to keep the longest carbon chain on vertical line. Second point, highest oxidation state carbon. Okay, I here wrote highest state, so please do a correction. Highest oxidation state carbon, the carbon which is having highest oxidation state, should be closest to the vertical top. Okay, it should be closest to the vertical top. Now, yes, in glucose, you can get it at the vertical top. In fructose, you will not, right? In fructose, it is CH2OH, CO. 1, 2, 3, 4, CH2OH, right, left. So fructose and glucose, this is D-glucose. And this I drew is D-fructose. D-fructose. Okay. So the highest oxidation state carbon here is this one. It is closest to the vertical top. Here it is this one. So it is at the top. Right? ठीक. So this is how it is done. Vertical line. So next point number 3, vertical line represents the bonds which are directed away from us. always, vertical lines always represents the bonds which are directed away from us, like this carbon, like this. Okay, so these are present on vertical line. If I say this is what a fissure is representing, then this is very apt. These two are, say, if I say here I have CH2OH, or rather I want to draw correctly, so I'll say CHO, CH2OH, OH and H. This will be translated to fissure as CHO, CH2OH. This vertical line pay this dash for, and this horizontal line H and OH. These are the wedge. The things which are on wedge towards us should fall on horizontal line. And cross section point of vertical and horizontal, this is the carbon. We don't have to mention the carbon separately. Is that clear? So this is how the conventionally correct method of drawing a fissure is. There is another wedge line, a wedge line dash representation. So wedge, this is the wedge, that is the bond coming towards us. This is our wedge. Okay. Then the dash, so yes, these bonds are directed away from us. And these bonds are, which are simple lined, okay, those which are simple lined, they are in the plane of paper. So if I'm using a simple line, so these are in plane of paper. Okay, if I have wedge like this, bonds coming out of paper, towards us. And if we have like this, then bonds away from us behind the plane of paper. Then these are directed behind the plane of paper. So, for example, if this is my diglyceraldehyde and I have to draw this one, okay, so this is the same. It is found that the diglyceraldehyde, coincidence, this is sheer coincidence. Don't take it as a rule that diglyceraldehyde, anyhow, there are only two possibility as DNL. There are only two possibility of RNS. It is just a coincidence that diglyceraldehyde is R in configuration. It could have been L also, doesn't matter. But it has been found to be D in nature. Diglyceraldehyde, this is diglyceraldehyde. L-glyceraldehyde, OH is on left. So this is found to be S. And the shorthand to apply RS in fissure is that the lowest priority group, you just ignore it. If that group is on horizontal, then in the end, we will interchange the answer. What answer? Let me say. So this we will ignore. The top priority group is OH. So number 1. This is number 2. This is number 3. So you draw an arrow for rest 3 groups. It is going R. But if the lowest priority group is on horizontal, then while reporting, this is S. So if the lowest priority group is on horizontal, then while reporting, you will report reverse of an answer. The arrow was going anti-clockwise. But if the lowest priority group is on horizontal, then your report is as clockwise. If the lowest priority group was on vertical line, then whatever the arrow is rotating, you would have reported the same direction. Okay, so for this one, this OH, CHO, see the arrow is going clockwise. So we will represent it as L-glyceraldehyde. Okay, because H is on horizontal line. In case, let me show you. Let us just assume, I am drawing randomly. If H is here and we don't know other things, किधर है? मैं random ही रख रही हूँ OH. So if I check now, lowest priority is vertical. Order is this. So this is reported as R only. So if this you can apply anywhere. Okay. So if the lowest priority group is on vertical line, then the two-dimensional arrow for rest three groups, okay, maintaining the CIP probability will be like this. Is that clear? ठीक, this is how it will move. So correct, the first type of question could have been asked is what is the correct representation of, say, it could be any monosaccharide, but let us say if they ask glyceraldehyde only. Okay, glyceraldehyde. So let us assume the option A. Now I'm drawing random. You have no idea. You have to identify D-glyceraldehyde. So if you could randomly select as RS, you just do the RS thing. Okay. CHO, OH, H, CH2, OH. Okay, C. If I have CHO, OH, H, CH2, OH, D. Representation could be any which way possible. CHO, okay, CH2OH, HOH, like this. So as we have just decided that all those which are D-glyceraldehyde will be R in configuration. So you will apply the shorthand. The priority order 1, 2, 3. Lowest is on horizontal. Arrow is getting anti-clockwise. So you will report it as clockwise. So A is one of your answer. Okay, come to this. First come to this fissure, then we'll go to wedge dash. So lowest priority is on vertical line. So you can directly draw an arrow. So R, this is also fine. Okay, here if we see, then lowest priority group is already on dash. Then the two-dimensional arrow for the rest three group is your answer. So this is S. So this cannot be D-glyceraldehyde. But if lowest group is not on dash, I have to write it as if it was on dash. And one exchange I have to do for that, right? So this is my hypothetical setting. Now from OH to CHO to CH2H, it is going S, but I will report it as R. So answer is D also. So answer which is D-glyceraldehyde? A, C and D. Okay, this is how you can analyze which particular carbohydrate is D-glyceraldehyde amongst the given structure. Is that okay? Next, let's move to next point. Haworth representation. Now, to understand the Haworth representation of monosaccharide, first you should revise the acetal hemiacetal formation of aldehyde ketone. So, if you have an aldehyde and you attack alcohol, first you will have hemiacetal. If you have one more mole of alcohol and you do that attack like this, then gem diether acetal is formed. Hemiacetal, acetal. Now, usually hemiacetal are extremely unstable, but hemiacetal with 5 to 6 membered ring structure are very, very stable. And so, in case of biomolecules, particularly carbohydrates, we have furan and pyran. Furan, when I have a 5-member structure, intramolecular formation, so one is oxygen. 6-membered with one oxygen, then it is called pyran structure. Okay. Now see, how is this formed here? Okay. How is this formed here? Yes, Sanjay, keep your doubts to yourself. Let me complete, then I'll ask in the end. Okay, you keep writing somewhere and in the end you can ask. So I was saying, now If I talk of D-glucose, as we have seen that the reaction is aldehyde, ketone and alcohol. Now I have one aldehyde and I have so many alcohols. And yes, there is a probability that other alcohols besides this can also attack. Let me see. This is my carbon number 1, 2, 3, 4 and 5. And this is my 6th. Okay. So I can have attack of 4th carbon. I can have attack of 5th carbon. If CHO is attacked by C4OH group, we will get furanose ring, right? And if it is attached by 5th, if CHO is attacked by C5OH group, this is OH, we will get pyranose ring. And pyranose ring is found to be more in stability, I would say, for glucose. In case of glucose, pyranose rings are found to be more stable. Is that absolutely clear? Pyranose rings are found to be more stable for this acetal formation. So if pyranose, 4th attack or 5th attack, so as we have decided, 5th is major. Now, how to draw the Haworth? Please listen very carefully. How to draw the Haworth? Haworth, there is a convention. There is a convention. Okay, now what is that convention? Right? Let me draw it entirely once again for you. Then we will discuss. Rather, I'll add a page because I'll like you to have it in your notes. See, the convention is for convention for drawing Haworth representation. How to draw this, right? Now, convention for drawing Haworth representation is, this is first regular sleeping hexagon you have to draw. Okay, with oxygen at vertical top, rather vertical right top, vertical right top for pyranose structure. Okay, and pentagon with oxygen at top like this for furanose structure. This is point number 1. Okay, number 2, draw vertical lines on each edge corner which represent carbon. Third, groups on the right hand side of fissure. Okay, right hand side of fissure will be placed below the ring on vertical lines and the groups which are on left hand side of fissure will be placed above the ring on the vertical line. This is the rule. This rule we have to follow. So now coming to this, as I said, my glucose will be, remember, right, left, right, 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 left, right, right. This is the setting of glucose. Right, left, right, right. And as I said that the major possibility is this oxygen will attack carbonyl. Now the point is, if this will attack, then this is closing the ring, but it is on horizontal line. We don't want the group to be on horizontal line. So bring OH of fifth carbon on vertical line. Now if I bring it to vertical line, my problem will be 1, 2, 3, 4. That okay, I brought it to vertical line. But what will be the position of this CH2OH now? If I simply do one exchange, I will change its configuration. But I cannot change its configuration. And if this goes, if this OH goes here, then this CH2OH will come here. That is one exchange. So I have to exchange it again to keep it configuration wise same. So this should be the arrangement of my fifth carbon. Rest remaining same. OH, H, OH, H, H, OH. Right? Now, this fifth carbon OH, if now attacks this sp2 carbonyl, there are two possibilities. Either the new structure will have this CHO as, just wait, a new chiral center is being created now. So C, I can have H, OH, or rather I'm drawing fissures, so I should not even write carbon. I should simply write 1, 2, 3, 4, 5 chiral center. 1, 2, 3, 4, 5 chiral center. This, of course, oxygen will be here and it is coming and forming a bond here. So you can put this oxygen here, or you can have this like somewhere in the middle. That does not have any importance. This is no carbon. Now here, this is my carbon number 1, 2, 3, 4, 5. Okay, sixth is here. But now how to place the rest? So I'll say rest will remain same. Number 2. This is 1, 2. 2 OH on the right, H on the right, OH on the right, H on the right. So I will just replicate this arrangement. Okay. Now fifth May on the left I have CH2OH, H, OH, H. And this CHO and either, now let me write with a different pen here. Either I will have this arrangement or rest remaining same. Okay, rest remaining same. I can have one more arrangement which is OH, H. So see, these two structures are exactly similar. The only difference that is there in them is that the new chiral center which is formed, okay, there is a new chiral center which is formed, is having OH in one to the right and one to the left of the vertical line of fissure. Otherwise, there is no difference. So these are called anomers. Okay, and this C1, carbon number 1, is the anomeric carbon, because on that there is a difference of configuration as H left and H right that way. Okay, so this is what I have described here, that you draw such structure. Okay, now when I want to draw Haworth, right? If OH is on the right hand side, I'm drawing Haworth of each. So if I say this is my structure number 1 and this is my structure number 2. So first I'm drawing the Haworth of 1. You draw simply a regular hexagon. Okay, then you start numbering 1, 2, 3, 4, 5. Now I'll draw vertical lines on each of this carbon like this. Okay, so I drew this vertical line. Right? Now I could have had one more arrangement. This 2 के लिए भी तो तैयारी करनी है मुझे. So for 2, I will do the same exercise. Okay, let me do the same exercise. Like this. Okay, I have to place here oxygen. So मैं space create कर दी. Oxygen. Is that clear? Oxygen is to be placed here. Now same way again I will draw the vertical lines. 1, 1, 2, 3, 4, 5. IUPAC numbering is also same. 1, 2, 3, 4, and 5. Now see, this is for structure number 1. So whatever on carbon number 1 on the right hand side fissure will go down. So OH is going down. H will go up. Number 2, OH is on the right. Up, down, up. H, OH. So H, OH. From this fissure, I'm translating. Fourth pe OH is down, H is up. Fifth pe H is down and CH2OH is up. Clear? Now for 10th, if I draw 10th, yes, so second. I think I could do rest same because we have only one place change done, na? OH, H, H, OH, H, OH. Only at this place, H coming here and OH coming here. So see, only carbon number 1, you have a difference, right? Is that absolutely clear? So coming to this is what is given in NCERT. Okay, so if OH and CH2OH are on opposite sides, if OH and CH2OH are on opposite side in a Haworth, or you can say if OH is on the right hand side in this conventionally correct fissure, then it is called alpha anomer of glucose. If it is on the left hand side, then it is called beta anomer of glucose. So this is my beta anomer of glucose and this is my alpha anomer of D-glucose. One more thing, remember, always for all D sugars, because it is all about conventionally correct and you will do the same thing, this sixth CH2OH is always on the upper side of the ring. Okay, always this sixth CH2OH in all D sugars in Haworth pyranose, बल्कि पायरेनोज क्या सभी में ही होगा ये, इवन फ्यूरेनोज में भी होगा. Haworth sixth CH2OH is always above the ring. Okay, and in L sugars in Haworth ऑफ तो लिखा ही नहीं अपन ने. In Haworth of D sugars. अदरवाइज इसका कोई मीनिंग ही नहीं है, राइट. Haworth of, आई एम क्रिएटिंग a स्पेस हियर ओनली ताकि आपके नोट्स में कोई इधर उधर गंदगी ना आए. Of D sugars, 6CH2H is always above the ring, and in L sugars, 6th CH2OH is directed below the ring. Below the ring. This is a rule. This is a rule. Why? Because, let me draw you. Again, I will add a page. So this is my alpha anomer of D-glucose. Okay. If we are asked what is the alpha anomer of L-glucose, okay, we are asked, so we will put a mirror here. Whatever is up will go down, na? Conventionally correct if we are talking, only then it is of some importance. Okay. So if I have to draw the Haworth of conventionally correct L sugar, or rather L glucose, so I will draw as oxygen. Now again I will draw these bonds. Whatever will be up will now be directed down, right? So position number 1, OH is up, is down, so now it will be up. Carbon number 2, OH was down, so up, and H will go down. Okay, carbon number 3, OH was up, will go down. Mirror image में reversal हो जाएगा ना. Position number 4, OH is down, so up. CH2H up, so it will go down, and H like this. Okay, so this is alpha anomer of L-glucose. This is alpha anomer of L-glucose. See, what is fixed? In alpha anomer, the anomeric carbon OH and 6th CH2H will be on opposite sides. Okay. In alpha anomer, OH of anomeric carbon and 6th CH2OH are always on opposite sides. That is fixed. If it is L-glucose, then CH2H is down. If it is D-glucose, then that CH2H is up. But anyhow, these are on opposite side. That thing will remain same. That is always fixed. So you can draw same thing for beta anomer also, right? If I want to draw for beta anomer, I can draw the structure for beta anomer also. Okay, so it is glucose ka pyranose structure. So it is called alpha D glucopyranose. This will be named as alpha L glucopyranose. Okay? Same way you can replicate the entire thing for this one also. Is that absolutely clear? If required, you can practice it on your own also. Same way. Same things will be repeated. Let me draw fastly just the answer. Okay, I would not discuss. I'll just draw the L glucose beta. I'm not now drawing very clearly or particularly fast. I'm just drawing. Okay, so in beta, this OH and CH2H are on same side. In L, it has to be in the bottom. So like this. H, H, O, H, O, H, H. This is your alpha. No, not alpha. This was beta. Beta L glucopyranose. Okay. If I have the same line to be repeated for these, here, if I want to replicate the same line for this, what should I say? In beta enomer, in beta enomer, OH of anomeric carbon and 6CH2CH are always on same side, are always on same side. Very important discussion we have just completed. When you will do the PYQs, you will realize how important it is. Okay. One more thing I want to add, that why beta enomer is more stable. So similarly, you can practice for Fisher also, for fructose also. Now, fructose has 5-member ring. Whatever we discussed was of pyranose glucose. If I want to do fructose, same thing, I will change the position. I will bring CH2H on horizontal line, OH on the vertical. We'll draw the structures. Now, see if it is alpha, then CH2H and OH, anomeric OH, are on opposite side. Okay. Anomeric OH is what we wrote. Na? So, this is the anomer. Carbon number 2 is my anomer. So carbon number 2 पर जो OH है, that should be used for identifying the alpha and beta name. I hope this is okay. है ना? In this beta, see this CH2OH and this anomeric OH are on same side. So fructose also. And again, if they want to have a L fructofuranose, you can draw the structures, but this will remain same. Now in L, this CH2H6 will go down. Okay. One more thing I was about to tell you. We went to fructose. Now, beta anomer is more stable than alpha anomer. That is what we say. Okay. Let me write. This is not for always. Huh? This is for glucose, I can say. For glucose, only. Huh? It may be different for different sugar. For glucose, beta anomer is thermodynamically more stable than alpha anomer. Now this is found. How it is possible? Why it is so? So let me take this alpha anomer first here. Okay, this is my alpha anomer. I want to draw its chair boat. 6-member, na? So I will draw its chair boat structure. For that chair boat structure, I will draw 2 parallel lines. I will connect with, say, oxygen I will place here. So I have drawn this structure and I will place oxygen here. So this is my oxygen. Now let me put 1, 2, 3, 4. So this is my carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. Okay. Next thing I will be having is axial equatorial. So that I will decide later. But first I'll just draw axial equatorial. So this is my axial, and this is equatorial coming outside. Axial going towards this side, equatorial, right? Axial, equatorial, axial इसका down जा रहा होगा, and equatorial like this. Okay. Now see, as this is a trans, if I see as it is a cyclohexane, position 1, 2, position 1, 2, these two, or rather you can say these two, if are on trans, then they have to be on equatorial, equatorial and equatorial. Again trans, equatorial, again trans, equatorial, cis, so axial. Axial equatorial on position 1, 2. So this OH is on axial. Okay, I will place this on axial and H. Carbon number 2, OH is on equatorial and H. OH is on equatorial and H. OH is on equatorial and H. CH2OH is on equatorial and H. So this was my alpha anomer, in which I have got one of my OH, that is the anomeric OH on axial. Okay, this was my anomeric OH. Now, same thing if you do again for your beta anomer. So, rest everything is fine. Na? If I repeat the same thing for this one, I'll say I can use this entire thing as such. The only difference will be my anomeric carbon. Rest, so no change it should be. Right? So I will replicate this, but with a change of this position. Rest all good. So what will be the change? I will say again opposite side. Na? So this is also equatorial, this equatorial, here this equatorial, equatorial and equatorial. All bulky groups are now at equatorial. Right? Here, if I say, then all OH are on equatorial. CH2OH is on equatorial. So when all groups are coming on equatorial, right, I can say all bulky groups are on equatorial positions. Is that clear? All bulky groups are on equatorial positions. So this is more stable. Is that clear now? That alpha anomer has one on axial, one OH I want to say. So it is less stable. Beta anomer has everything on equatorial. So it is more stable. Is that clear? Okay, no problem. Moving further now. So this is all about alpha and beta anomer. Now, how further questions could be asked? Alpha and beta, alpha form has melting. This, yes, you have to remember if you can remember, because in mains it has been asked, and this line is given in NCERT. Right? This line, alpha and beta anomers for particularly glucose, which is commonly called dextrose or typical sugar. So alpha and beta, alpha form has melting point of 419 Kelvin and beta has a 423. So beta, which is more stable, has higher melting point. Glucose is also called dextrose. Okay. So I think till here, formation of Haworth for particularly glucose I have discussed is all clear. So let us have a doubt session for 5 minutes till here. हम जिस भले जितना ही पढ़े हैं, but उसमें कोई doubt हो तो raise your hand. I have one hand raised. No, I have so many hand raised. I have to check. Wait. Let me see. So Sanjay was initially also there. Yes, Sanjay, please tell.
Ma'am, the furan structure that you drew there is not correct, ma'am. It is tetrahydrofuran, not furan, ma'am.
So who said it is a furan? We said the structures are related to furan, so furan no structure.
Okay, ma'am. You were in that context. Fine, ma'am. I was thinking about the fundamental structure of the molecule. So.
Yeah.
And another one, ma'am.
Yes.
Ma'am, in case if there is no any acetyl carbon for that for a particular sugar, then alpha beta anomerism cannot be defined for it.
Then what will be there in place of hemiacetyl carbon in the Havoc?
Example CH2, ma'am. Just CH2, nothing, no substituents there, and like we just like skip one carbon and we'll have like an OH group or
Then I doubt it is a sugar even. If there is CH2 at that place, then probably there was no carbonyl over there,
okay, ma'am.
right? Then the relevance for this whole thing is not there.
Okay, ma'am.
Okay, Shyam. No, Shamal. Okay, Shamal is still unmuting. Okay, Sai Dhanush.
In the chair form structure, I don't understand why you took trans as equatorial and cis as axial.
Actually, for that, you have to read the anomers of cyclohexane and GI in cyclohexane. So I have shared the notes of that also with your center principal. Please ask them. They will give you.
Yes,
Okay. Okay. So now, Shamal, can you unmute yourself?
Yes, ma'am.
Yeah.
Ma'am, I wanted to ask what does plus minus signify? Like D plus, it was written L minus. So what does
Dextro
it
and
mean?
levo. Dextro and levo. If we say capital D bracket में plus, it means it is a D sugar but is dextrorotatory. L bracket में plus मतलब it is a L sugar but is levorotatory that way.
So, ma'am, capital D and dextro does not have any relation in this context.
Yeah, I have
Like,
already said that in the
yes,
DL.
ma'am. I just wanted to make sure.
Yes, yes, certainly. No relation.
Mm. Thank you, ma'am. Thank
No
you, ma'am.
correlation. Okay, Shrey.
Actually, my doubt was same, like dextro and levo and capital D.
Okay, okay, so it is done.
Yeah, yes. Thank you.
Okay. Anyone else? Anyone else till now, whatever I have taught, any doubt? Anyone else? Okay, no one it seems. Okay, so then let's move further because now we are entering to another very important topic called muta rotation. Now, what we have seen that there is an open structure for glucose I'm talking, then it goes to cyclic structure alpha or it could go to beta. There is an equal probability. Now, if these are present in aqueous conditions, then as you know that hemiacetals can open to aldehyde ketone and can again go to cyclic. So there is an equilibrium. So even if I start with 100% pure of alpha anomer through cyclic structure, it will be converted to beta anomer. Right. If I start with beta, it will go to open chain and these are all in simultaneous equilibrium with each other. So they will always end up at a particular temperature, a fixed composition. And it is found that in this equilibrium, this open chain is just like a pathway. It is not a major component. It is hardly 2%. So I would like to ignore it. That how much it is, let us ignore it. Now it is found that pure 100% alpha anomer, if was there in the solution, will have specific rotation of 112 degrees, right? That to dextro. If I have 100% beta anomer, its specific rotation is plus 18.7 degrees. So both are dextrorotatory. Beta anomer is also dextrorotatory, alpha anomer is also dextrorotatory. But when I mix them, then at a particular temperature, they will always have a fixed composition, and that fixed composition has a specific rate rotation of plus 52.7. Okay, how much? Plus 52.7. Now, if I know this, it means there is ultimately a fixed value of percentage contribution of alpha anomer and beta anomer. Okay, how this is happening? Because hemiacetal is unstable. That is why this is happening. Now, how to calculate how much is this and how much is this? As I'm talking of percentage, I can say, assume, okay, let us assume alpha anomer is X percentage, right? Then beta anomer is 100 minus X percentage, right? So what is this final plus 52.7 net value? I'll say 112 dextro multiplied by X plus 18.7 multiplied by 100 minus X, and total has to be 100 because we are talking of specific rotation, right? Should be equal to plus 52.7. This is how the mixture of both alpha and beta should behave. And I have this value already, that 52.7 is an experimentally confirmed value. Solving this, we get that alpha anomer is 36% and beta anomer is 64% in this equilibrium medium at room temperature. Is that absolutely clear? If I'll change the temperature, definitely the composition will change. But this is what we are talking of, room temperature. So I start from any of the anomer and I end up at a fixed specific rotation value for the equilibrium mixture. This phenomenon is called muta-rotation. Okay. Now for muta-rotation, for compound, let me write here, for compound to show muta-rotation, for compound to show muta-rotation, there has to be a compulsion. Muta-rotation, it should be in hemiacetal form. It should be in hemiacetal form. This is a compulsion. For a compound to show muta-rotation, it should be in hemiacetal form. Compulsorily वो hemiacetal form में होना चाहिए. Then only it can open na, and it can come back to another anomer. Acetals do not show muta-rotation. Muta-rotation. Now what is acetal? If I want to show you what is acetal, as we were drawing all these structures, right? Whichever I take, say I take this one, alpha anomer. Okay, I take this alpha anomer here and I place it here. If I treat it, this alpha anomer with methanol under slight acidic conditions, you know this is hemiacetal. This will react and will result in formation of acetal. See, I will do the cheating because writing repeatedly will just waste our time. So this will become OMe. And once this has become OMe, this is acetal. Whether a given structure is acetal or not, you have to screen each carbon. Like this carbon, it has one oxygen carbon attachment, one OH. Then it is acetal. See, this carbon has oxygen carbon and oxygen carbon. So this is acetal. Is that clear? So this shows muta-rotation. This structure will show muta-rotation. Muta-rotation. But this structure, acetal, will not show muta-rotation. I hope this is absolutely clear. Okay. Now let us go to the chemical preparations of glucose, how you can prepare glucose. So first is by boiling alcoholic solution of sucrose with dilute HCl or dilute H2SO4. Now what is sucrose? Sucrose is a disaccharide. There are two monosaccharides present in it. Okay. Now, as we have already seen how these are reactive, how these are the structural feature of this monosaccharide. Okay. So how to form a disaccharide? When we form disaccharide, The reaction used is, we have so many OH groups, na? One molecule OH, another molecule OH in some reaction method or whatever undergo dehydration, and a new ether linkage is formed. This is called glycosidic linkage. It is basically an ether linkage. So see here, when I am saying 1 alpha D glucose. So alpha, it means this OH is on the down and this OH is on, this 6CH2H is on the up. So it is alpha. This is the anomeric carbon. It's OH, and fructose ka C2, which is also anomeric. Okay. Now, whether it is beta or not, you can see the 6th CH2OH and this 2OH, carbon number 2OH is directed downside. This is the glycosidic linkage. When we hydrolyze it in presence of water, like ether hydrolysis, this will undergo hydrolysis and I will have alpha D glucose and I will have beta D fructose. Okay, what are the products obtained? I obtained alpha D glucose and I obtained beta D fructose initially, but they will always have a muta rotation. So this is not the specific rotation of alpha D glucose. See, alpha D glucose kuch nahi hai, there is no. What we have is a equilibrium mixture plus 52.7, the muta rotated. Same for muta rotation of beta D fructose, we found this minus 92.4 value. Is that absolutely clear? Now the sucrose initially is dextrorotatory. It was dextrorotatory, and when the reaction completed, we get 1 mole of dextrorotatory glucose, 1 mole of levorotatory fructose, and see, resultant mixture is levorotatory. क्योंकि 1 mole ना 92 is minus and is dominating. So resultant is levorotatory. This is called inversion of sucrose, as it inverted its optical rotation from dextro to levo. And the product mixture is called invert sugar. It is extremely sweet in taste. Sugar, invert sugar. That is why it is called invert sugar. Is that absolutely okay? So this is one method of preparing glucose. Another method is by hydrolysis of starch, which is achieved by boiling starch with H2SO4. If you have a starch, you boil it with H2SO4 at temperature 393 Kelvin under pressure. This is the commercial method of glucose preparation. Same, you hydrolyze those glycosidic linkages and you get glucose. Chemical properties of glucose. Now, glucose give all these chemical properties. First, this is our structure of glucose. So it will have definitely combination of aldehyde and hydroxy groups. So if I treat it with HI, very important, it is reduced to N-hexane. Total reduction to N-hexane. If I have NH2OH, oxime is formed at aldehyde. Nickel hydrogen reduction I do, this CHO will become CH2OH. So we'll have glucitol or sorbitol. What is it? Glucitol or sorbitol. If I treat it with HCN, I will have cyanohydrin. CHO becoming CN and OH, cyanohydrin. If I put acetylation, then all this OH will become acetate. Alcohol plus acetyl chloride. So pentaacetate is what I obtain. But remember, this is what I have talked of open chain structure. Those properties which are for its cyclic structure, if I try for Schiff's reagent do not open its hemiacetal linkage, and no, we do not have any reaction. Cyclic structure, do not give Brady's reagent test. Do not give NHSO3 test. Acetylation, yes, still, because you see 1, 2, 3, 4, 5. So still you have a pentaacetate of D-glucose. But once pentaacetate is formed, then you do not have this oxime formation. And it can show mutarotation. All these reactions are possible for glucose cyclic structure. Next is the enolization, tautomerism, and isomerization of glucose, let us see. So I have a D-glucose, right? If I place it in dilute OH minus, this carbon alpha, this can tautomerize to enol. And when there is no effect on the rest of the molecule, it remains as such, right? When this tautomerize, then again, when it retautomerizes to carbonyl, there are three possibilities. It can go back to its aldehyde stage, but when it goes, this chiral center number 2, which is now sp2 in enol, right? In enol, it has become sp2. So when it is going back to sp3, I have two possibilities. This OH on the same as it was position or on the other side. So if it is on the same, I'll say again D-glucose is obtained. If it goes on the left hand side, then we have a D-mannose. Mannose means these two OH are like this. In glucose, it is right, left, right, right. In mannose, it is left, left, right, right. Or what if this OH, this enol tautomerizes and I have a ketone? So D-fructose is obtained. Rest the same. This is a D sugar only, na? Sorry. D sugar only, na? OH is always on the right hand side, bottommost. So what we have is fructose and glucose are functional isomers of each other, right? Fructose and glucose. I started with glucose. I have fructose. One is aldose, one is ketose to function. And D-glucose and D-mannose are C2 epimers. Carbon number 2 पे difference है, rest configuration same. So we have enolization, yes. Tautomerization, yes. And then isomerization. So we could get the functional isomer and we could also get the stereoisomers. Next comes the oxidation of monosaccharide. Now that depends on the oxidizing agent that we use. For example, if I use bromine water, remember bromine water only oxidizes aldose to acid. No effect on ketone. Fructose is not oxidized to acid or any method. Only this CHO is oxidized to CH. No effect on CH2H. And bromine water will get decolorized. So this is the practical organic chemistry test of aldose and can be used to differentiate aldose sugars from ketones. Those sugars which will give this test will be aldose. Those which will fail this test will be ketose sugars. Second is nitric acid dilute HNO3 oxidizes both 1 degree CH2OH and CHO. Okay, to acid. So I have glucaric acid. Glucose se glucaric. General name for all aldose sugars acids will be aldaric acid or saccharic acid. So HNO3 oxidizes CHO and CH2OH both. Then comes the HiO4, but HiO4 we have done in polyhydric alcohols, right? Each vicinal alpha hydroxyaldehyde, OH, and don't take that they are on opposite side because this is simple, this is not a cyclic structure. It can have rotation, OH, OH will break each bond and put OH, and then this is very important reaction in our this week chapter. Biomolecules, right? They may ask that how many moles of HiO4 are required by glucose. This was D-glucose. So D-glucose required 5 moles of HiO4, formed 5 formic acid and 1 formaldehyde. D-fructose required 5 HiO4, formed 2 formaldehyde, or sorry, 5 formaldehyde and 1 CO2. Okay, you just keep on breaking. OH, this is becoming H2CO3, na? This center. So H2CO3 will be like CO2. See, gluconic acid if they give, then alpha hydroxy acids do not react with HiO4. So I will not put there this fission and rest we will write like this. Okay. Then comes the test with Benedict's or Felling or Tollens. So aldehyde if react with Ag plus forms silver. Cu2 plus they become copper plus brick red or orange. Hemiacetal linkage on opening if forms aldehyde or alpha hydroxy ketones, then they will give these tests. Okay, hemiacetal linkages on opening if form aldehyde or alpha hydroxy ketones, तब ये test देंगे. When concentrated H2SO4 instead of oxidation dehydration takes place. So if I take glucose and I treat it with concentrated H2SO4, then we get a carbon black. So it is like as if it has absorbed all its H2O and only carbon is left. Next, we go to disaccharides. The disaccharides which are given in NCRT, you have to remember those. Like what points to remember? Which are the monosaccharides? So in sucrose, it is the alpha D glucose, beta D fructose. What are the site of linkage of glycosidic linkage? C1 of glucose and C2 of fructose. Whether it is a reducing and non-reducing sugar. For identifying reducing or non-reducing, you simply have to check exactly same as mutarotation. You have to find in the entire molecule, is there any hemiacetal linkage? If there is any hemiacetal linkage, then you just tick as a reducing sugar. Okay, like in here, no hemiacetal because these are my anomeric carbons and these are both acetals, so non-reducing. Maltose. This is alpha D glucose, alpha D glucose. C1 of alpha D glucose combined with C4 of alpha D glucose. Now C4 is used, so this C1 is left as hemiacetal, so it is a reducing sugar. If I go to lactose, then I have beta D galactose and beta D glucose. Both are beta this time. So this CH2OH and carbon 1 OH are upside. CH2OH and carbon 1 OH are upside, same side, right? We have one hemiacetal linkage left, beta D glucose, so it is reducing. Okay, this is how you will check. Similarly, if I go to polysaccharides, starch is from C1 to C4 glycosidic linkages. Okay, it is monomer is alpha D glucose, like this alpha D C1, C4, C1, C4, C1, C4, it keeps on joining. Starch has two components, one which is water soluble, it is called amylose. It is only 15 to 20% of total starch. It is a linear polymer of C1, C4 linkage. Next is amylopectin, in which linear amylose is further linked to one more linear chain, from where this C6 and C1, okay, like this, next it is joined. It is 80 to 85%, it is water insoluble. Linearly, it is still C1, C4, and branches are from C1, C6 linkages, like this. Okay. Ethanol is commercially prepared by the oldest method of fermentation of sucrose. Sucrose, invertase sugar you put, invertase enzyme you put, you will get glucose fructose. Inversion हो रहा है ना, glucose and fructose obtain हुआ तो. Zymase, then it is fermentation, ethanol is formed. Next polysaccharide is cellulose. It is plant starch. Linkage is C1, C4. C1, C4 of beta D glucose. Glycogen, it is called animal starch. It is like amylopectin. What was amylopectin? This one. Linear is C1, C4. Branch is C1, C6 of alpha D glucose. Okay. Test of carbohydrate. One is the Molish test. I have added the entire reaction also. So you take a monosaccharide, add Molish reagent. But what is Molish reagent? It is 1-nephthol dissolved in ethanol. 1-nephthol is alpha nephthol dissolved in ethanol. Okay. And when we put concentrated H2SO4, we get a purple ring at the junction of the two liquids. If you shake, then the ring is gone. It will be distributed. So what happens? Reaction. I have monosaccharide. Okay. This type of monosaccharide. So it forms a cyclic ring closure. And at what positions? I will say 1, 2, 3, 4, 5, 6. So dehydrates from C2 and C5, C2 and C5 like this, like this. So this linkage will be created, and then this OH and this OH dehydrate to create aromaticity. So So you get furfural. If R is hydrogen, then it is called furfural. If R is CH2OH, okay, or 5-hydroxymethyl furfural, then you call it 5-hydroxymethyl furfural. Now this when treated with alpha naphthol, where is alpha naphthol? It is in the Molish reagent, and you will get that unstable dark purple condensation product. Okay. And this test is given by pentose and hexose only, not all smaller monosaccharides cannot give. Starch iodine test. Starch when added to iodine, you get a bluish black color. Fehling-Benedict tolerance, we have already said, reducing sugars. If they have hemiacetal, we'll have this test. Next, we come to Barford test. It is an important test to differentiate monosaccharide and disaccharide. Okay, so it is an important test to differentiate between monosaccharide and disaccharide. Now, what is the test? Reagent is copper acetate in acetic medium. It is slightly acidic. Rest reaction and all same as Fehling, that is copper 2 plus will be reduced to copper single plus. Only monosaccharide give briquette precipitate with the reagent in 5 minutes of heating. Disaccharides do not give this test. So this is a test only for monosaccharide. Then comes the Selevinov test. These are all given in NCERT lab manual, so you have to do them. It is the test given only by ketose sugars. Like for aldose sugars, we had, where is this? Bromine water test we wrote na initially. That was for aldose sugar. And for ketose sugars, we have Selivinov. It is test given by only ketose. Selivinov reagent this time is resorcinol with concentrated HCl. Ketose sugars under acidic medium first form furfural. We just did this furfural thing like this. They also form furfural. Okay. Which form colored complexes with resorcinol. Ketohexoses give cherry red complex and ketopentose give bluish green. Ketohexose gives cherry red complex and ketopentoses gives bluish green complex with resorcinol. Okay, I have added all these questions for whatever we studied. You can please try these questions, and that will help you to understand whatever we did, how it has been asked, and how to apply. Okay, so let us come back to the doubt session. Yes, please raise your hand if anyone has any doubt after what we discussed previously. I could not see any hand. Is there anyone? Okay, I got Prajnadeep. Yes, Prajnadeep, please tell.
Ma'am, can you repeat the fourth and fifth tests for carbohydrates?
Fourth and fifth test. Let me check. Fourth is this Barford, right? So yes, Prajnadeep. Barford mein basically it is same as we did na that reducing property thing, but the reagent is special, copper acetate in acetic acid. Okay, and this test was found to be given only by monosaccharides, not by disaccharides. So copper 2 plus will be reduced to copper single plus. Cu2 plus is reduced to Cu single plus. 2 plus is blue. Cu single plus is red. Okay, so when this test happens, we get this change of color, and we confirm that it was a monosaccharide.
Okay.
And fifth test is a Selevinov. This is given only by ketose. You have to remember the
Ma'am, what is
Selevinov.
given by that aldose sugars?
Repeat, what is?
Molish. What is given by only aldose sugars?
Only aldose sugars. We do not have any here specific test in this zone. We did it here. Just wait, bromine water test we did na. this. Bromine water decolorization is given only by aldose sugars.
Oh,
Okay.
okay, ma'am.
Bromine
Okay.
water only for the aldose, Selevinov only for ketose. Let's repeat. Molish for general all, है ना?
Okay, ma'am.
Pentose and ketose will give molish.
Ma'am,
Right?
what is that furfural
Furfural.
in the Selevinov test?
Yeah, it was this. This is furfural. Here we wrote. If R is H, furan pe CHO is furfural.
Okay.
Okay. That is called furan. Here I have written R is H, then it is called furfural.
Okay, ma'am. Thank you.
Tomorrow we'll complete our protein part. Okay. And day after tomorrow we have to do nucleic acid and what is the other one? Vitamins.